A cycle GAN allows you to do something like this. So we've got a horse, and we can convert it to a zebra. Okay, that's what we're going to kind of be looking at for our example. Converting a picture of a horse to a picture of a zebra. In this case, it was a video of a horse to a video of a zebra. The same idea. And the idea of this is that we're actually going to have two different generators. If we just think of the problem, right, the problem is we've got a picture, it's got a bunch of background, and then it also has a horse with a bunch of background. And our goal is to turn this picture into a horse picture, but keeping all of the same background. Of course, with neural networks that know nothing about horses or nothing about zebras. And our goal is to do this with little label data. The label data, in fact, that we'll have is we will have horse pictures and zebra pictures. But the horses and zebras are going to be different, right? We're not going to have the two animals, a horse and a zebra, both in the same configuration, facing the same way, and everything else. So how's this going to work? We're going to have a zebra generator, and we're going to have a horse generator. All right, so we've got a zebra generator. The zebra generator is going to take in a horse image, and it's going to output an image, hopefully with the horse replaced with a zebra. Similarly, the horse generator is going to come out with an image and is going to take in a zebra image. And our goal is to train this horse generator to the image that it outputs should be a horse image, which is basically this image and replacing the zebra with a horse. And then we have discriminators. So we have a discriminator for zebras, and this just takes in an image. This image can either be the output of G sub z, or it can also be one of our actual zebra pictures, and it comes out with values between 0 and 1, right? Where 0 means not a zebra, and 1 means is a zebra. We do the same thing for a discriminator for horses. The horse discriminator takes in an image. It can be either the output of the horse generator, or it can be a real horse picture and outputs values between 0 and 1, where here it's not a horse and this is a horse. So we know how to train the zebra generator to generate zebra images that will fool the discriminator. We know how to train G sub h to generate horse images that'll fool the horse discriminator. Here's the problem, though. We need to ensure that if we've got, let's say, this is a horse image, and this horse image is coming from one of our real horse pictures, and we have got, let's say, our horse over here at the top left. Let's say this is the bottom left, actually. So we're down here. This is our not very good looking horse. And what else do we have on here? We have, let's say, a tree. That's maybe a sun, actually. We'll make a tree. And we have birds. Well, when we feed this through G sub z, right, which takes a horse image and tries to produce a zebra image, it could produce something that looks like this. And with these stripes, right, to represent that it's a zebra. So we have this striped image. It doesn't even need to be in this orientation. It might be facing right. And there might be no trees, and no birds, and no sun. If this is a good enough zebra to fool the discriminator, then GZ thinks, I've done a great job, right? GZ thinks, I took an image, I created a zebra image. But unfortunately, as far as it's concerned, it doesn't actually care about the input image. It can just be treating this as a source of randomness, right? I've got a bunch of random pixels, I'm going to create a zebra. If I have different random pixels, I'll create a different zebra. But there's nothing that says, actually, you're trying to take the horse that is in here and replace it with the zebra and leave everything else alone. So we're going to need a little work to do that. We're going to have to adjust our loss function. So keep in mind, when you are solving a problem, there's really, using neural nets, there's three things you have control of. You have control of the data. You have control of the architecture. And you have control of the loss function. Those are the three things that are going to really control what you're going to be learning. Right? There's also a bunch of hyperparameters you're going to have to choose to make the learning work well, but this controls what you're going to be learning. In our case, we know our data. It's these labeled horse and zebra pictures. We know the architecture. We're going to be creating four different neural networks, probably convolutional, and then the question is how we're going to do our loss function. And the loss function is control what gets learned. In our case, if we just use the loss, as we talked about with the GAN loss, then we're going to be learning to create reasonable-looking zebras and create reasonable-looking horses, right, that are sort of indistinguishable from our real crop of horse and zebra pictures, but we won't get the effect we want of making sure that the horse and zebra get replaced and nothing else gets replaced. So that we're actually sort of replacing a horse with a zebra. That's our goal. So we're going to do that by working on the loss function. And here, the way we really need to think of it is our loss function is twofold. So our loss function consists of two things. Fool the discriminator. This, in this case, is our loss function for g sub z. So when we're trying to change g sub z, we want to make sure it's coming up with a realistic-looking zebra. So this is, again, negative loss of d sub z of g sub z of our image. So of our horse image. Not only do we want to do that, though, we want to make sure that the horse image and the zebra image are like one another. We could do some sort of a mean squared error between the horse image and the zebra image. That's something, because that would then encourage us to go ahead and leave a lot of it the same. So we could go ahead and leave the birds there, we could leave the sun there, we could leave the tree there, and get rid of the horse and put in a zebra. But there's a trickier solution. The trickier solution is this. We go ahead and we feed this into dz, and here we get some output. Our loss function will depend on this. That's this part here. We're also going to feed this zebra back into GH. And we're going to see what sort of an image do we get out of this. And our hope is we get an image that looks like the original. And then we do a mean squared error between these two. So that is, we do not look at a mean squared error between the horse and the resulting zebra image. Because we know there should be some differences between those, right? The horseness and zebraness will cause some mean squared error. Instead, we say, what if we took the horse and took it on a cycle? We took the horse down and created it and converted it to a zebra and then converted it back to a horse. And now we can compare how does the horse original and the modified horse look. So we are taking, this is in the horse space, and this is in the zebra space. We take the horse into the zebra space with g sub z. And then, from here, we take the zebra back into the horse space with g sub h. And then we look and we say, okay, what is the difference between the original horse and the round-tripped horse, or cycle horse, and this is the cycle. So we're looking at the difference between h and g sub h of g sub z of h. And we're trying to minimize that difference. Clearly, in this case, if this is the zebra we end up with, then it's very unlikely that we're going to get back to this horse. But we're looking at this mean squared error, and so we now have, if we look at our loss consists of this mean squared error here. This calculation goes back through g sub h and g sub z. So when we are propagating this error back, we are actually going to be updating the weights of both g sub h and g sub z, because if we look at this mean squared error, we don't know whose fault it is. Is it g sub h's fault? Is it g sub z's fault, or both? And so we're going to update both of them as we go back. So as we propagate the error, right, the loss is we fool the discriminator, and we also minimize round trip mean squared error, which is going to ensure that it looks like the same thing. Or we hope it ensures that. So we are going to be ensuring that if we take a horse and we convert it to a zebra and convert it back to a horse, that we end up with close to the same thing. We've also got to make sure the other way around. So if we have a horse and we're in the horse space and zebra space, and we have a particular zebra, and we take over to the horse space, and then we take that horse back to the zebra space, we want to ensure that this distance is also small. So we're going to do training on both sides of this. Right. So when we are training the zebra generator, we are going to ensure that not only does it fool the zebra discriminator, but also that when we round trip and go back through the horse generator, that we end up with something close. And we're going to be training the horse generator that when we have a generate a horse, right, so this is g sub h and this is g sub z, that we are going to take a zebra to a horse, and then we will make sure we fool the horse discriminator, and also that when we go back using the zebra discriminator, that we end up with somewhere close. That is the idea of cycle GANs. So we are going to be learning to do this picture sort of replacement of a horse with a zebra, or a zebra with a horse. And all we have to begin with are horse pictures and zebra pictures. That's all we have.